Okay, let's look at some different examples of hypothesis testing. So in this first problem, a basketball player has a career free throw percentage of 53.3%. He works with a trainer to improve his technique. The next season, he's able to make 26 out of 39 free throws. Test the claim at the 0.05 level that the player has improved. Okay, question number one is, what type of problem is this? Mean, proportion, variance, or standard deviation? Here, kind of the giveaway is that we have a percentage here that we're going to use proportion. So, as usual, we'll start with the claim. He claims that the player has improved, which means that the proportion has gone up, meaning it's greater than 0.533. Now, it's not going to be equal to, because if it's equal to 0.533, then that means he hasn't improved. It would be the same. Let's use the critical value method, and then we'll look at the p-value method. So, state the hypotheses. The claim does not contain equality, so we move it to the alternative. The null will be the complement or opposite. In this problem, we have x, the number of successes, is 26. N, the total number of free throws, is 39. Alpha is 0.05. Okay, since we're talking about proportion, we're going to use z. This is greater than, which means that this is a right-tailed test. Now, we need to know the z value that separates the rejection region from the fail to reject. The alpha value is 0.05, which means the area to the left is 0.95. So if I want to find this value, we need the area to the left, which is 0.95, and we can use the inverse norm function in the calculator. Inverse norm, let me write this out. Area to the left is 0.95, comma 0, comma 1. .645. Okay. Let's find the test statistic. X bar minus mu over sigma over the square root of n. That's the wrong formula. We're using proportion. So the formula we're going to use, p hat minus p over square root of p q over n. Now in this problem, we don't have p hat. Doesn't mean we can't find it. It's x over n, or 26 out of 39, which is 0.667. The population proportion is assumed from the claim, which is 0.533. To get Q, we do 1 minus 0.533, 0.467. N is 39. 1.57. Now, the critical is 1.645. The test is 1.57. That will land over here on the left. So, our decision, therefore, we fail to reject the null hypothesis. Conclusion. Does the original claim contain the condition of equality? No, it does not. Do you reject the null hypothesis? No, this way. Do you reject the null hypothesis? No, we fail to reject. There's not sufficient sample evidence to support the claim. Okay. There's not sufficient sample evidence to support the player's claim that the free throw percentage has increased. And we're finished with the problem. Now, if you were going to use the p-value method for this problem, then you're welcome to. What you would do is get your curve. It'll still be right-tailed. The area in this tail is the p-value. The test statistic that we got was 1.57. Now, to find this area, we would use the normal CDF function. The left-hand boundary is 1.57. The right is forever, so it's 999, 0, 1. 0.0582. So we compare the p-value, 0.0582. The alpha value was 0.05. This is greater than the alpha value. Therefore, we fail to reject. Okay. Moving on. Question 2. A local newspaper reports that the mean cost of a speeding ticket was $150. The local police claim that amount has increased. The police collect sample data from 160 drivers who have been fined. The sample group paid a mean of $154 per ticket. Assume the population standard deviation is $17.54. Is there sufficient evidence to support the police claim? All right. Now, clearly we're talking about the mean in this problem. The police claim that the amount has increased, meaning greater than $150. Now, we're not going to say equal to, because if it's equal to 150, that doesn't mean it's increased. State the hypotheses. The claim does not contain equality, so it goes in the alternative. The null will be less than or equal to 150. Okay, we have a sample size of 160 tickets. The sample mean is $154. Now, the population standard deviation, sigma, is 17.54. Now, this is important. Because we have sigma, it means we'll use the z distribution and not the t. Alpha is 0.01. Sketch the picture. This is greater than, so it'll be a right-tailed test. And we need to know the critical value that separates reject from fail to reject. Okay. The alpha value is 0.01, which means the area to the left is 0.99. If we use INV norm for 0.99, 0, 1, 2.33. So that's the cutoff for reject or fail to reject. Let's find the test statistic. Sample mean is 154. Population mean is assumed from the claim. 150. Sigma is 17.54. N is 154. .83, which is greater than the critical value. Therefore, we reject the null hypothesis. Therefore, reject the null hypothesis. Conclusion. Let's go to our diagram. Does the original claim contain the condition of equality? No, it does not. Go down. Do you reject the null hypothesis? Yes, we do. The sample data support the claim. The sample data support the police claim that the mean ticket fine has increased. And we're done with the problem. Now, if you wanted to use the p-value method, it would be very similar to the previous problem. Still a right-tailed test. The area in the tail is the p-value. The test statistic is 2.83. We'll use normal CDF to find this area. 2.83, comma, 999, comma, 0, comma, 1. .0023. So that's the p-value. The alpha value was 0.01. The p-value is smaller than the alpha value. Therefore, reject the null hypothesis. All right. Moving on. What's next? Question 3. Efficiency is very important at the U.S. Post Office. The standard deviation of line wait times nationally is 7.2 minutes. The local post office believes it is more efficient. The local post office samples 25 random customers and finds the standard deviation to be 3.5 minutes. Test the claim the local post office is more efficient than the national average at the 0.1 level. Okay. In this problem, we're talking about efficiency. So we're saying how much time do the postal workers spend with each customer. We want the standard deviation to be small. So state the claim. We're claiming the population standard deviation. Let's see. They say it's more efficient. So they want to say less than 7.2 minutes. State the hypotheses. This does not contain equality, so we move it to the alternative. Greater than or equal to 7.2 for the null. N is 25. Sample standard deviation S is 3.5. Alpha equals 0.1. Now, since we're talking about standard deviation, we'll use the chi-squared distribution. Because the alternative is less than, this is a left-tailed test. Now, we don't use the p-value for the chi-squared distribution. We only use critical value. So this is reject. This is fail to reject on the right. Okay, the alpha value is 0.1, but chi-squared distribution needs area to the right. So the area to the right is 0.99. N is 25, therefore degrees of freedom are 24. So we go to the table. We go to the 0.99 column and we go down to 24. 10.856. Let's find the test statistic. N minus 1 S squared over sigma squared. N is 25. Sample standard deviation is 3.5. Population standard deviation is assumed from the claim. .67. That is smaller than 10.8. So we reject the null hypothesis. Decision. Reject the null hypothesis. Conclusion. Does the claim contain equality? No, it does not. Go down. Do you reject the null hypothesis? Yes, we do. The sample data support the claim that. We should say the local post office's claim. that the standard deviation, make sure you get the parameter in there, of wait times is less than, what was it, 7.2 minutes. And we're done with the problem. Okay, moving on. Question 4. The amount of water consumed by Montana residences is normally distributed. A random sample of 10 Montana residences was taken with a mean of 120.3 gallons and standard deviation of 10 gallons. Test the claim that the average amount of water consumed is not 125 gallons. Use the significance level of 0.05. Okay. It's clear in this problem that we're talking about mean. They claim the mean is not 125 gallons. State the hypotheses. The claim does not contain equality, so we move it to the alternative. Now, in this problem, we have a sample size of 10, a sample mean, x bar, is 120.3. The standard deviation, S. This standard deviation comes from the sample, which means we need to use t-distribution instead of z. This is not equal to, so it's a two-tailed test. Let's find the critical values that separate reject from fail to reject. The alpha value in this problem is 0.05. So if we go to our table, we're doing two tails. The alpha value is 0.05, so we use the center column. N is 10, therefore degrees of freedom are 9. Center column, go down to degrees of freedom of 9, 2.262. Positive on the right, negative on the left. So now we know the cutoff for reject or fail to reject. Find the test statistic. X bar minus mu over S over square root of n. Sample mean is 120.3 minus the assumed population mean is 125. S is 10, N is also 10. Negative 1.486, which is going to fall in between the two critical values. We fail to reject the null hypothesis. Therefore, fail to reject the null hypothesis. Conclusion. Does the original claim contain equality? No, it does not. Do you reject the null hypothesis? No, we fail to reject. There is not sufficient sample evidence to support the claim. Whose claim is this? This is the to support, we don't say whose claim, we'll just say the claim that the mean water consumption is not, what was it, 125 gallons. And we're finished with the problem. Now, if you wanted to use the p-value method here, you could. Still using t, still going to be 2-tailed. The test statistic was negative 1.486, so it'll be positive 1.486 on the right. The p-value is the area in the tails. We can find the area in the tail using the t-CDF function. So let me look at the right tail. 1.486, comma, 999, comma, degrees of freedom, or 9. .0857. This is not the p-value. This is the area in this tail. The p-value is the area in both tails. So we have to take this number and times it by 2. 0.171. The alpha value, 0.05. The p-value is greater than the significance level, therefore we fail to reject the null hypothesis. Okay. Let's look at one more of these. Question 5. The U.S. Mint sets the standard for coins. The Mint states that the standard deviation of the weight of pennies must be less than 0.023 grams. A sample of 37 pennies are collected, and the sample standard deviation is found to be 0.01648 grams. Test the claim that all pennies are within the U.S. Mint specifications at the 0.1 level. Okay. Clearly, we're talking about standard deviation in this problem. State the claim. We're claiming that it is within the standard. So we're claiming the standard deviation is less than 0.023 grams. State the hypotheses. This does not contain equality, so it goes to the alternative. The null will be greater than or equal to 0.023. Because we're using standard deviation, we're using the chi-squared distribution. Okay, let's find the critical value. The alpha value is 0.1. Now be careful. That 0.1 is the area in the tail. Chi-squared distribution is the area to the right. So 1 minus that would be 0.99. In the sample size is 37 pennies, which means degrees of freedom are 36. Okay, so the area is 0.99. We go to the 0.99 column, go down to degrees of freedom of 36. Now you're not going to see 36 in the table. We're going to go to the closest one, which is 40. 22.164. That will be the cutoff for reject or fail to reject. Let's find the test statistic. N minus 1, S squared, sigma squared. 37 minus 1 times S, sample standard deviation, was the 0.01648, the whole squared. Assume the population standard deviation from the claim is 0.023 squared. (18.48), which is less than the critical value. We reject the null hypothesis. So decision: reject the null hypothesis. Conclusion: all right, if we go to the diagram, does the original claim contain the condition of equality? No, it does not. Go down. Do you reject the null hypothesis? Yes, we do. The sample data support the claim. Support the claim that pennies, I say all pennies, are within the, let's see, specification that the standard deviation of weights is less than 0.023. And we're done with the problem. In the next video, I'll be going through the rest of the problems on the handout.